Hello everyone! Today, I am excited to share our research on saliency-guided foveated video encoding for low latency and immersive cloud VR. In this work, we tackle the fundamental trade-off between visual quality and bandwidth in cloud VR streaming by moving beyond traditional gaze-based foveation and introducing a fully AI-driven, saliency-aware pipeline. Let us start with the background. Cloud VR offloads heavy 3D rendering to powerful edge servers, enabling high-fidelity experiences on lightweight headsets. The system works by first collecting the user controls from the client and send it to server for game execution and rendering. Then the game frame will be encoded and sent back to client side. This brings benefits for enabling graphically demanding content on lightweight devices. However, Cloud VR introduced new challenges. First, ultra-high resolution and extremely low latency are necessary for providing immersive experience. Secondly, the wireless and mobile network face bandwidth limitation, network variation, and packet loss, which makes the mobile VR experience challenging. To survive in these challenges, foveation-based optimization techniques are widely explored. Foveation is a key feature of human vision system. Our eyes focus on a small center and receive most information from this area and omit the details in peripheral region, which means for a given frame, user may not even notice a change of quality in the peripheral region. So based on this feature, foveation-based optimization leveraging non-uniform acuity of human eyes to optimize the bandwidth usage. Foveated video encoding helps in saving bandwidth usage in cloud VR system. Traditional FVE uses an eye tracker to allocate high quality to the center of the user's gaze while aggressively compressing the peripheral vision to save bandwidth. This brings us to our core motivation. Traditional gaze-based FVE has a fundamental flaw. First, it requires built-in eye trackers, limiting widespread deployment across heterogeneous devices. Second, and more importantly, it is entirely content-independent. Human attention is naturally drawn to visually salient stimuli, like a sudden explosion, bright colors, or fast movement. If a highly salient event happens in the user's periphery, traditional FVE will have already compressed it into a blurry, blocky mess. When the user's eyes instinctively dart to that event, they are met with jarring visual artifacts, which destroys immersion. This gap inspired our solution. What if we track the content instead of the eyes? We propose a gaze-free, saliency-guided streaming pipeline. Here is our system architecture. We extend the traditional server-side pipeline by introducing a novel, visual saliency modeling module. Once a game frame is rendered, this module instantly predicts which regions possess high visual saliency. This probability map is then fed into the video encoder to dynamically allocate bits. By prioritizing bandwidth to the most salient parts of the scene regardless of current gaze, we protect peripheral cues and eliminate the need for eye-tracking hardware entirely. Integrating this into a live cloud VR system introduces a massive challenge. The saliency inference must occur after the frame is rendered, but before it is encoded. This means the eye sits directly on the synchronous critical path. In VR, the motion-to-photon latency budget is extraordinarily tight. If our saliency model takes 10 or 20 milliseconds to run, it will inflate the end-to-end delay, negate any benefits of foveated encoding, and cause motion sickness. We needed a network that was practically instantaneous, yet highly accurate. To achieve this, we designed a highly specialized, ultra-lightweight deep neural network. First, we heavily downsample the input frame and use EdgeNext Small to extract hierarchical spatial features. But static images are not enough. Video saliency depends heavily on motion. Standard 3D convolutions would instantly break our latency budget. Instead, we introduce a spatial reuse temporal shift-gated recurrent unit, or SRTSM, GRU. This module takes a slice of the hidden state from the previous frame and shifts it into the channel dimension of the current frame. This parameter-free channel shift allows our model to maintain a streaming temporal memory across frames, with effectively zero added computational overhead. Finally, we decode the features using ghost convolutions, which halves the floating point operations relative to standard convolutions. With the raw saliency map generated by our network, the next critical step is translating these probabilities into a video encoding strategy. If quality drops abruptly between a salient and non-salient region, the user will see banding or halos. To prevent this, we first apply a Gaussian blur to the map, enforcing spatial smoothness. We then map these values to the encoder's quantization parameter, or QP. Using the constant Q mode with delta QP, we assign a lower QP, meaning higher quality, to salient regions and a higher QP, meaning lower quality to non-salient region. A hyperparameter called QP offset bounds the maximum compression difference, which prevents to produce noticeable visual artifacts. Now, bringing it all together as shown in this figure, a rendered game frame is downsampled and passed through our ultra-fast DNN to generate the saliency map. This map drives the QP allocation, which is fed directly into NVIDIA's hardware encoder. The result is a final encoded frame that saves massive bandwidth by compressing the non-salient periphery, while preserving crystal-clear visual fidelity, exactly where human attention demands it. We evaluated our system on a Meta Quest 3 streaming over Wi-Fi. By focusing on elegant system design, our results speak for themselves. First, our saliency model is phenomenally efficient. It requires only 0.3 gigaflops and runs in just 1.4 milliseconds per frame. Second, despite adding an I-inference step, our single-pass encoding strategy actually results in a lower overall server latency than baseline systems. Third, we achieved a massive 68% improvement in perceptual quality metrics compared to gaze-based foveation, all while saving up to 43% in network bandwidth. To ensure our objective metrics translate to actual human experience, we conducted an IRB-approved user study. We recruited 15 participants with varying levels of VR experience to play games streamed to a Meta Quest 3 headset. They evaluated our system against standard ALVR and the gaze-based FOV optics across 5 subjective dimensions. The results were striking. As shown in the distribution of Likert scale responses, our saliency-guided pipeline received the highest proportion of positive feedback. Crucially, Kruskal-Wallis tests showed that our method significantly outperforms the baselines, with a p-value less than 0.05 in both overall visual quality and spatial smoothness. By smoothing the quality transitions based on content, we successfully eliminated the jarring visual boundaries that plague traditional foveated rendering. All of this was achieved without compromising temporal coherence or gameplability. In conclusion, our findings demonstrate a clear paradigm shift in cloud VR. You do not need expensive, device-specific eye-tracking hardware to achieve highly efficient perceptual video compression. By understanding what intrinsically draws human attention, our lightweight AI selectively compresses frames at ultra-low latency. Furthermore, we found a strictly monotonic relationship between the QP offset, visual quality, and bandwidth throughput. This controllable trade-off provides a direct mechanism and paves the way for dynamic, adaptive bitrate streaming in fluctuating network conditions. We will be releasing our source code publicly to help drive this research forward. Thank you for your time and attention.